Let's talk about the first law of thermodynamics. This simply states that energy cannot be created or destroyed. I want to talk about the first law of thermodynamics by using an example, Mike and Ike's. The first time I taught this class, for some reason they really loved Mike and Ike's, so that's what's in this lecture today. So if you take 3 pieces of Mike and Ike's, you can look at the box and see how many calories that is. So according to what it says on the box, that's about 18 calories, which is 75.3 kilojoules. If you were to eat these candies, how would you use this energy? How long is it going to last? This is going to depend on a variety of things, including your basal metabolism, so that's how much energy you spend just sitting around, heat loss to the environment, depending on the temperature of the room, and also if you happen to be expending a lot of energy like walking, running, etc. If you're in class, sitting still, taking notes, you're going to lose heat to the environment, and in addition to your basal metabolism. Let's think just about that heat loss, and let's think of how long it's going to take you to expend the energy that you gained in those 3 pieces of Mike and Ike's. By the end of this video, you should be able to do some basic heat balances that assume steady state, so no change in temperature of your system, and also consider convective radiation or convective heat loss, radiation, and also a conductive heat loss. So heat loss can happen through a variety of ways. So it can occur through convection, conduction, or radiation. You might have seen these in a physics class. So convection is energy transfer between a solid surface and an adjacent liquid or gas. So in this case, you're the solid surface and the air is moving around you, and you are going to be losing heat to that air. So I'm going to start by just writing down what we've done so far. So the first law of thermodynamics says that energy can change forms, but it's not going to be created or destroyed. In many ways, you can think of energy balances kind of like you think about mass balances. You see that this is very similar to the law of conservation of mass. Again, we're going to say that we eat 3 candies, and that's going to be 18 calories. And we find that by looking at the box. And remember that this is calories with a big C, which is different than calories with a small c. So this is 75.3 kilojoules that we can get from these 3 candies. So our heat loss, or you could also say heat transfer, is going to be due to convection, conduction, or radiation. So what I'm going to do is go through and I'm going to describe how you can get heat transfer quantities for each of these. First, we'll do convection. So again, in the case of this example, that's you. You are the solid surface sitting in the room, which is full of air, and you are losing heat to that air via convection. In order to figure out how much heat you're going to lose to convection, you need to find a convective heat transfer coefficient. So you can look these up for various situations. This one that I have written here happens to be for a fully clothed human. And you can see that this heat transfer coefficient actually does depend on the change in temperature between the person and the room, the air that they're sitting in. So I'll go ahead and I'll calculate our convective heat transfer coefficient. And before I do that, I'm going to say that the room is going to be 21 degrees Celsius and the person is going to be 37 degrees Celsius. So our HC, our convective heat transfer coefficient, is just going to be 1.222 times the temperature difference raised to 0.299. And when I solve this out, I end up with 2.8 watts per meter squared Kelvin. So if I'm looking for the rate of convective heat transfer, I'm going to use this following equation. Well, the convective heat transfer coefficient was for this particular example with a fully clothed human. This is just the general equation for convective heat transfer or heat loss. In this case, we're warmer than the environment. So you're going to be losing heat to the environment. So our convective heat loss is going to be our heat transfer coefficient times the surface area. In this case, it's going to be the surface area of a person, so like your skin surface area, or your clothed skin surface area, and then the difference between your body and the room that you're in. So if I solve this out, I already have my heat transfer coefficient. The average surface area of a human being is 1.8 meters squared. And then I've got my temperature difference, which is just the temperature difference between body temperature and the room. So when I work this all out, I get 80.6 watts. So basically, we're losing heat at a rate of 80.6 watts, joules per second, to the environment due to convection. So you can also lose heat due to radiation. So this is energy that's emitted by matter in the form of electromagnetic waves. So the cool thing about radiation is that it doesn't require any sort of medium. So it can occur in a vacuum. If you think about the sun's energy traveling to the earth in a vacuum, it happens via radiative heat transfer. So we need a few things to figure out how much radiation we're emitting. So to figure out how much radiation we're emitting in our example, we're going to use this Stefan-Boltzmann law. So here the radiative heat loss is going to equal epsilon times sigma times the surface area times the difference between the temperature of the surface and the temperature of the environment, where both of those are actually raised to the fourth. So in this equation, epsilon, this thing that looks kind of like an E, is the emissivity. And you can look up emissivities for different types of materials. Sigma is going to be the Stefan-Boltzmann constant. And that is always going to be the same, 5.67 times 10 to the negative 8 watts per meter squared Kelvin raised to the fourth. So for this example, I will look up the emissivity of a clothed person, which is 0.9. And then I'll use my Stefan-Boltzmann constant. The area is going to be 1.8 meters squared. And then I'll use these same temperatures that I used before to calculate convective heat transfer. And remember, for this equation, you do need to have temperature in Kelvin. And when I work this out, I end up with 162 watts. So this is the amount of heat that we lose, or the rate of heat loss of due to radiation to the environment. And then finally, you might lose heat to conduction. So this is any sort of transfer of energy from more energetic particles to less energetic particles. And basically, this has to do with the temperature difference between two things. So you have heat transfer from warm to cold. So I'll write out the equation for conductive heat loss here. So we basically have Q, which is our rate of conductive heat loss, and that's going to be a constant times the area over which this heat loss occurs, times the difference in temperature and the difference in distance. So you can think of this as like conductive heat loss like through a window, where the delta T is the temperature on each side of the window, and then delta X is the thickness of the window. So KT is our thermal conductivity of the material. That'll be in watts per meter per Kelvin. A is the surface area again. Delta T is the temperature difference between two sides of the material. And then delta X is going to be the thickness of that material. For example, in meters. So for the sake of this example, where we're looking at eating candy and then losing heat to the environment, conduction doesn't really apply here. So we're not going to consider conduction for the sake of this example. We're only going to consider convection and radiation. So our total heat loss to the environment is going to be the sum of convection and radiative heat loss. And I've got to go back and look up those numbers. So convective heat loss was 80.6 watts. And then the radiative heat loss was 162 watts. So I add that together and I get 243 watts. So you can think about this and think about the equations that we used for convection and radiation. I mean, you might think about how your heat loss would change if the room is hotter or colder. And what you might find, or what you would find, is that if there's a bigger difference between your body temperature, which really has to stay within a pretty narrow range, and the room, you are going to have greater heat loss. So the next question is, how long is the energy from the candy going to last? And so we can basically divide the amount of energy in the candy by the rate of our heat loss. And so we looked at the box and we saw that we had 75.3 kilojoules, which is 75,300 joules. And then we calculated that we're losing about 243 watts to the environment. So a watt is the same as a joule per second. And we do this division and we find how many seconds the energy in the candy will last. So it's going to be about 310 seconds, which is about 5 minutes. So you eat 3 pieces of candy and you can warm yourself in a cooler room for about 5 minutes. So you can think about so how, what's this going to change? So if the room is is colder, then the candy isn't going to last as long. If the room is warmer, provided it's not much warmer than your body temperature, then the energy from the candy could heat your body for a longer period of time. And you might have noticed this, how maybe you find that you have to eat more, if you're spending a whole lot of time in the outdoors when it's cold. This is why. So I want to do one more example today, which is an example of cooling a room. And so if you're thinking about how much you have to cool a room, you can think about heat sources in the room. And if we're thinking about kind of our typical classroom, heat sources could include people and lights. You've probably been in a situation where you were in maybe a stuffy room with a whole bunch of people, and the room got really warm and uncomfortable. And so this is kind of the situation we're looking at. So if I am looking at a kind of an energy balance, I can look at the rate of change of energy in the room. This is going to have to do with the temperature of the room. And then I can look at all of the energy transferred into and out of the room as heat. And I can also look at the amount of energy that leaves the room due to work. And this is just kind of a convention that you see, is that work is an outflow and then heat is an inflow. But the signs of these terms would change depending on the actual direction of heat or work. So for this example, our room doesn't really do work. It's just a room. And we're also going to assume that the room is at steady state. So the energy, the amount of energy in the room, that is the temperature, doesn't change with time. And so basically, I want to just make sure that I have no differences, or like all of my heat inputs into the room equal my heat outputs from the room. So what I'm basically doing is I'm setting the all of the heat flows equal to 0. And all of my heat flows are going to include the generation of heat by people or students and lights. I'm going to consider some convection. So I'm going to say that the outer wall of the room is cold, and we have some convective heat loss there. And then I have this air conditioning system. So basically how much cooling power is what it's going to end up being, is needed to offset the generation of heat by students and lights. So in the previous example, I calculated that each person is going to contribute 243 watts. And I'm assuming that we have 10 people in the room. I'll also say that we have 14 watts, or 14 lights that emit 100 watts each. A lot of light bulbs are very inefficient, and much of their energy is lost to heat. And so I see that the amount of heat generated in our room is going to be about 3,800 watts. And so here I have our equation for convection. And basically I've just taken a convective heat transfer coefficient of 12 watts per meter squared Kelvin, which is typical for a wall. And then I've said that the room is 294 Kelvin, and the temperature of the inside of that outer wall is 283 Kelvin. And so I do have a mistake here, so that should be Q dot for convection. And I end up with a negative number, negative 270, and that's because the temperature of the inside wall is cooler than the room temperature. So in fact, we will, instead of, so the students generate heat, but the wall cools the room. And so that's why that's going to be a negative. So just for consistency, I'll change that to a positive up there because the number that we calculated was negative. And so basically the AC has to offset the heat generated by the people in the lights, but it doesn't have to work as hard because it's cool outside and that wall is a little cool, which helps the AC out. So this is kind of another example of how, your energy requirements for a building are going to change with the seasons. So we find that our AC needs to provide basically a cooling power because of the units that, or the sign that we used above of 860 watts. And so whenever you're doing these kind of equations, just be really careful with your, positives and negatives. Okay, so that concludes all of the material for this video. So basically we talked about 3 different types of heat transfer: convection, conduction, and radiation. I gave you some examples of equations for convections, which use a heat transfer coefficient that you need to figure out, radiation, and then also conduction. And then finally we can do an energy balance, where we said we had no work, no change in temperature of the room, and so we had to balance our heat generation. So that concludes this introduction to energy balances. So now you should be able to apply this concept of energy balances in order to calculate radiative, convective, and conductive heat loss in systems where you don't have any work and you don't have any accumulation of energy in your system. That is, the temperature of your system isn't changing with time.